Hi. So this talk is about tooling, and many talks here have been about the language, but I'm going to talk more about tooling and the standard library, and that's where most of the focus are going today. Most of the tooling that I'm talking about here is coming bundled with the language. Yep. So what's happening today? We have 1.0 coming out this summer. It will bring a lot more stability to the language. We will start using semantic versioning, which means that we will only have breaking changes between major versions. We also have Elixir Conf, which is the first conference. It's happening in Austin, Texas in July. And we will have some great speakers. Jose Valema, of course. We have Dave Thomas, Bruce Tate, and Robert Verding. We've also just released a package manager called Hex, which I think will be a big step for the community and also for the entire ecosystem. So these are the topics I'm going to talk about today. I'm not going to go into much detail about every topic. I'm selecting a few features from every topic that I think are interesting, and I will talk more in detail about. First up, we have Mix, which is our build and project management tool. It handles your dependencies. You can integrate it into your projects with the help of Mix tasks. And then we have Hex, of course, that also integrates into Mix, which is the package manager. Next on, we have Interactive Elixir, or IEX for short, which is the shell. We also have XUnit, which is the testing framework. And from the standard library, I will talk about streams and how we're beginning to extend OTP. So first off, we have Mix, which is the build and project management tool. You use Mix to generate new projects. It of course compiles your code. You can use it to run tests. It will handle your dependencies, and also whatever else you can think of, because you can extend Mix. So immediately after you have installed the language, you will have Mix available to you. You can call. Just need my pointer. You can call Mix new immediately with the project name, and it will generate the project structure. You will have your Mix file, which configures your project. You will have some config files, some code files, and some tests. Then you can immediately just go into the project directory, call Mix test. It will compile your code and run the sample test. Mix.exs is the Mix file. It is generated with the help of Mix new. It is used to configure your project. And here's a sample project configuration. It's the application name, the OTP application name, the version, and an optional requirement on which version you want. Yeah, like I said, Mix compiles your code. It takes your .ex files and generate beams and the app file. It can also compile Erlang code, so you can have your Erlang source directory. It will find those files and it will compile them. It will also compile Erlang, Elixir, and parser files. And the Mix compile task is fully pluggable, so you can have dependencies which can add their own compilers. And you can define and you can add those compilers in your project configuration, and those will be called when you call the Mix compile task. This is how you define dependencies. You can see here that we have defined a dependency that we will fetch from GitHub. We can handle Git dependencies and path dependencies. Git dependencies, I think, are self-explanatory. path dependencies are a dependency that is located on your local file system. So you just define the path to the dependency, and it will be treated as a part of a project. And this is useful when you're developing a new feature or fixing a bug, and you want to try out that in another project without committing it in Git and pushing it to GitHub and so on. So here we define how to fetch poolboy. If you look at Ecto, we didn't define how to fetch it. That means it will be treated as a hex package, which I will go into more detail later. So we have all the mix tasks for handling your dependencies. You can fetch dependencies, update dependencies, and so on. We also have the dependency converter, which is internal to Mix. It is what converts your dependency tree into a flat list of dependencies, which are ensured to be unique. Because you can have a dependency, so you can have a dependency, for example, poolboy, which two other dependencies depend on, and we need to converge that into a single dependency. And you can have conflicting definitions of poolboy, so one project may fetch poolboy from GitHub, another may fetch it from Bitbucket or something like that. So in that case, we have a conflict, and you need to explicitly override that conflict in your project. If not, we will raise. If the definitions for the poolboy dependency are not conflicting, we will converge them into a single dependency. We also have repeatable builds, which means basically that all the users of a project will get the same versions of every dependency. So we achieve that by when the first time we fetch the dependency, we write the version that we fetched into a log file. This log file is included in your version control. So every user of a project will get this log file when you deploy code, you will get this log file, and that will make sure that you get the exact same version of the dependencies that you used when you tested the project. We can also handle rebar dependencies. We can compile rebar projects, and we will fetch and handle children of rebar dependencies. So if the rebar project have defined their own dependencies, we will treat them as normal dependencies in Mix. You can also extend Mix. This is what it looks like. You just define a module, which is prefixed with Mix tasks, and then the name of the task. And you also need a run function of R81. After this module is compiled and is a part of your load path, you can just call the task like this, and it will print out hello world. So that's a really nice feature. These are two projects that are extending Mix through Mix tasks. The first one is Ecto. It's a library for interacting with databases. And like any good database library, we can handle migrations, which is a way to ensure that your database is on the same version as your code. So you can roll back and roll forward migrations, which will, if you're using a SQL database, it will create table, create indexes, or drop tables, and so on. So like the Mix new task, we can call ecto-gen migration to generate a new migration file with the necessary boilerplate, and then we can use the ecto migrate task to migrate to the latest version or roll back to an older version, and so on. Another cool project is called XRM, which is a project for generating OTP releases. I believe it uses Relax under the hood, but with the help of Mix, when you call the Mix release task, it can gather the metadata from the project configuration, the OTP configuration, and so on, and it can use that to generate the final release. We can also extend other parts of Mix, apart from adding tasks. Like I said, you can extend the Mix compile task. You can add SCMs. SCMs are like how we fetch the dependencies, like I told you we support JIT and path, but you can add more ways to fetch dependencies if you want. We also support umbrella projects. An umbrella project is a project which has many child projects that are located in the apps directory. The child projects are isolated, which means that you should be able to go into the child project and it should work like any other project. You should be able to pull out the child from the umbrella and it should just work. So that means that we have no config inheritance between the parent and the child project. And umbrella projects are useful when you have like these big projects, but you want to separate it into different OTP applications, but you don't want to split it out into different repositories. The umbrella tasks are recursive. And like I said earlier, the umbrella project is not an OTP application. So, for example, when you call mix.compile, it doesn't compile the umbrella project. It instead recursively goes through your dependencies and compiles them. And we also have the mix run task, which loads your project and starts it. And it will load and start all the children. So it works like a single monolithic OTP applications, but you can treat it separately when you want to. So, the package manager Hex. Right now, it only works with Elixir packages, but you can publish Erlang packages and Elixir packages, of course, but you cannot fetch. So it only integrates into Mix right now. So you cannot fetch packages from the Erlang world, but that's something we're working on. We want tooling in the Erlang world. For example, by integrating to Rebar or having an e-script or something like that that can fetch your dependencies. This is what the Hex website looks like. Here we browse documentation. You can find documentation and browse packages. We also have download statistics, which you can use to gauge how used the project is, which I think is really useful. A Hex package is basically a tarball with source code and some extra metadata to describe the package. When the package is published, it's pushed to the Hex API, which in turn pushes it to Amazon S3. By having all the packages as tarballs and the registry file, which is an index of all the packages on Amazon S3, we can get very high availability, which means that if the Hex website were to go down or the Hex API were to go down, you can still deploy your code, all users can still use Hex. The only thing that would stop working is publishing packages. So these are the tasks that Hex adds to Mix. You can list them. Mix local is used to list locally installed tasks. And Hex is installed as a code archive. For those who don't know, an Erlang code archive is like a zip file with compiled modules, which is if it's added to the code path, Erlang will just treat it as a directory with the modules as files. And when Mix starts, it will find this. It will find these tasks in the load path, and it will load them, and we can list them like this. And all administrative tasks are done through this command line interface. You publish packages, you register your user, and so on, because the website is only used to browse packages essentially. We also have the dependency resolution, which is, I would say, the core of Hex. Before the dependency resolution runs, it fetches the registry file. The registry file is an index that contains all packages, the package's releases, and the releases dependencies, and the version requirements on the dependencies. All version requirements use semantic versioning, which means that we can set sane version requirements without getting breaking changes, at least hopefully. So the dependency resolution is an algorithm that finds the latest version of every dependency that satisfies all the version requirements on a specific dependency. And when the dependency resolution runs, we need to use the log file again to make sure that we have repeatable builds, and we need to honor overrides of dependencies. For example, since it's a dependency resolver, we can fail the resolution, which means that for a dependency or for multiple dependencies, we cannot find a version of the package that satisfies the requirements, the version requirements that you have on that package. So you need to be able to override that in your top-level project. So future work that we want to do on Hex, Erlang support, of course, and we also want to be able to install executables, probably through e-scripts that are globally installed. Yeah. So next on we have interactive Elixir, or IX for short. It's the Elixir shell. It's built on top of the Erlang shell, so we get all the cool features from the Erlang shell, like remote shells and the diagnostics and stuff like that from the Erlang shell. I will not talk much about IX. I will just show some features that I think are pretty cool. First on we have IX-S mix, which you can call on the command line. So it starts IX with the mix application or with mix loaded. So what this does is, when you call mix like this, it will use the default task. The default task here being mix run, which, like I said earlier, loads your puts all your dependencies and your projects in the load path. So it loads them. It starts all the applications and the whole OTP application tree. Also loads OTP configurations. So this is really useful. So it should be easy to get the shell started with all your applications loaded. That should not be hard. You should not use some arcane command line flags and stuff like that to just start a shell with your application loaded. Next on we have pry, which is a way to hook into a running process with a shell. It is inspired by the Ruby tool, also called pry. And this is the easiest way to show how pry works, is to show an example. So here we have a shell session. We start by spawning a process. In this process, we assign a variable, just as an example, and then we call the IX pry function. And when this code executes, we will get the user of the shell will get this request. So it's asked if you want to pry the specified process, and we of course say yes. And at this point, a new shell is started with the context of this that is at this pry call. So we get so this shell exists in this process, and this process is blocking while this shell is running. So we can get access to the process registry. We can get access to local variables like this. We can call binding, which lists all variables as a keyword list and their values, and so on. So that's really useful to debug stuff. And you can also use this from tests. So if you have some failing tests, you can add the pry to your code where you have the bug, and you can get a session where you can inspect why things are going wrong. Elixir has first-class docs. With that, we mean that docs are in line with the code. So we have, in the source code, we have, for every function, you can define documentation for it. And when the Elixir file is compiled to a B module, the documentation is included in the with the bytecode. So this means that we can get the documentation at runtime, and we can do cool things like the h helper here, which you call with a function name, and then you get the documentation for the function. We also have tab completion in the shell, meaning that if we, for example, write enum.m, you can tab and it will auto-complete to map or show possible suggestions. So you can basically browse the documentation in the shell, which is really cool. We have other helper functions like h here. We have the r helper function, for example, r for reload. So you give it the module name, and it will recompile the module's source code and reload the module. So it's really useful when you're debugging something. So you have an open shell session, you change some code in your source file, you do R with the module name, and you have the new module up and running. So next on with XUnit, which is our testing framework. Like with IAX, I will not talk much about how XUnit works. I will just show some features from it, which I think are interesting. First off, we have the assert macro, which if you have been to an Elixir talk, you've probably seen it. Assert is really powerful. Just like normal assertation functions in testing frameworks, it basically checks for true or false, or in this case where we're doing a matching, it checks if the match is successful. Since it's a macro, it can look at the structure of this code, and we can do stuff like extract parts of it. So this is the assertion, and we quote the assertion to get the structure of the code. So this is the Elixir AST, and this looks kind of complicated, but it really isn't, and you don't have to understand it to get the example. Basically what you need to see is that we have the matching operator here. The first argument is the left operand, the OK tuple. The second argument is the call to the foo function. So with this, we can extract the foo call and do it separately, so we can get the value of evaluating the foo application. We can get the value and do this match with a case construct instead of just using the match operation, which will just fail with a bad match error. So since we can extract the foo call, we can get these beautiful failures. So we can pretty print the code like this. And as I said, we can extract the foo call, so we can get the right-hand side of the expression here. So unlike if we were not using an assert macro, this expression would just fail with bad match. You would not see why it failed. It would just be this opaque failure, and you would have to investigate what the foo function is returning and so on. But here we can print exactly why the match failed. So that's really cool, I think. I believe Dave Thomas worked on these beautiful colors and stuff like that. Right, we can also tag tests. It looks like this. This is a test function. You tag it with an atom. Here it's integration. So with this you can tag certain tests or test cases, which you can then filter on. So if you have some expensive integration tests which are by default excluded, you can then include them with include flag. You can exclude some tests, and you can only run some specific tags. You can also call mix tests with a file name, and a line number. The line number here being the location of the test, so this is a useful way to run just a single test. And if we go back to the failure here, you see that we include that exact same expression, so you can just copy paste this to the mix test call, and it will just run that test. We also have Doctests, which are from Python. So here we have the documentation for the map function, which maps a function over a collection. So here this is just a description of what it does, and here we have some example code. You see that the example code takes the form of a expression you would write in the shell. So here it's prefixed with ix, the expression, and the expected value of the expression. So when the test suite runs, we will execute all the example code that takes this form in your documentation and match it, so we check that it doesn't raise, of course, and we'll match it against the expected value. And this is really good because it ensures that your examples are up to date, and also your documentation becomes part of your test suite. So next on we have the standard library. I will talk about streams and how they integrate into certain parts of OTP. And I will also show how we are beginning to extend OTP in some places. So streams are composable, lazy collections. They implement the enumerable protocol, which all collections in Elixir implement. But more things than just collections implement the enumerable protocol. For example, I/O devices can be treated as streams, so they will also implement the enumerable protocol. And to show this, I will first show an example of how you would read a file line by line and execute a function for its side effect for every line. So first we open the file, returning an I/O device, pass it to read device. The read device is recursively calling itself, reading from the device line by line until we reach end of file. And for every line, we are executing the operation function for its side effect. So this is a lot of code to just read a file line by line, I would say. It's a lot of unnecessary code. It's hard to really, unless you are really explicitly, or you're reading this carefully, it's hard to see what really happens. But streams can remove a lot of this boilerplate. So we have, this is the corresponding code with streams. So we have the file stream function, which creates a stream from the file name, and we pipe that to the enum each functions, which executes a function here. This is the function, operation function that you saw in the previous example. It executes that function for every element in the enumerable, and we're executing it for its side effect. So this is really nice. We are removing a lot of the boilerplate. What's also nice is that when we call this function, the file is not opened. Since it's a stream, which are lazy, the file is only opened when the stream is forced. So when you call an eager function on the stream, enum each here is an eager function, so it will be forced immediately and open immediately. But we can use the streaming functions here to compose a set of operations over the stream and then later force it. And then while we're composing this stream, the file will not be opened. We can also use streams with GenEvent. So it's quite easy to imagine a GenEvent as a stream of events. So we call the GenEvent stream function on a GenEvent handler. We get the stream as a result. And since streams, like I said, implement the enumerable protocol, all functions that work on that protocol can be used with the stream. So we can take the next 10 events, which will block until 10 events have arrived. We can also use it with the comprehensions, because comprehensions now use the enumerable protocol. Yeah, so that's it about streams. I will also show how we are beginning to extend OTP. And first I want to say that OTP is really great. It's very powerful. You can do almost anything with it. But it doesn't have many high-level abstractions. So we have GenServer to create servers. We have GenEvent to create event handlers and so on. So we are starting to look at other languages, for example, Clojure and Akka, how they are creating some high-level some abstractions that are higher level than what exists in OTP. One of those abstractions is agent, which is an abstraction around state, inspired by Clojure. An agent builds on GenServer. So we get all the nice things by it being an OTP process. We get error reporting, we get code upgrades and so on. But it has reduced functionality from a GenServer. So we only care about the state. We do not care about message passing. We don't need to implement handle info, handle cast, handle call, and so on. We only care about state. So this is an example for how agents works. So this is a cache module. This is a cache. In the start link function here, we call the agent start link functions, which starts an agent process. We pass a function that initializes our state. Then we can put values into our cache by updating the agent state. And we can also get values from the cache by giving it the key, and we extract a part of the state with the agent get function. So, as you can see here, we're always passing functions to the agent module. So that's how we reduce the handle info and handle callbacks and stuff like that. So this is the entire API for a shared cache. And I don't think I have to show you how much code this would be if you were using GenServers, where you would have to implement all the callbacks like handle info and so on. So this is really nice, I think. Like most of the Elixir standard library, you can use agents from Erlang. So first off, we have this a bit strange defines. We do this to remove the Elixir dot here, because when Elixir compiles, it translates its module names into Elixir dot the module name, because we don't want conflicts with the normal modules that exist in Erlang. So this is what it looks like. Apart from the defines, it's a pretty straightforward translation from the Elixir code. Yeah. I will also talk a bit about tasks. A task is a small single asynchronous action. It's just a process that you can spawn and then await the result from it. either by it crashing or you get a successful return value from it. And it's not a complicated concept. It's something that is pretty easy to accomplish with normal processes. But what's nice with patterns like this and GenServer and GenEvent is that they are easily recognized. It's not just that we don't have to re-implement the code. So when I see GenEvent, I know that it's about event handlers. When I see GenServer, I know it's about some state that is handled by a server and message passing to that server. And when I see tasks, I know it's about a small single asynchronous action. Yeah. And this is how you use tasks. You call the task.async functions, which spawns a new process with executing the work, what is happening in the do some work function here. Then we can continue with our normal process until we are awaiting the result from the task. So a task can return a value or crash. So here we wait for the monitor message or a successful run of the task.
Just a quick comment. In a minute, Kenneth officially starts. I went long, so I'm going to go 10 minutes long here. So I encourage you to stay, but you may be a little late to Kenneth's talk. Anyway, so don't worry, don't sweat it.
Yeah, I'm just starting to finish up anyway. So I've gone over many things today. But what I wanted to show with this talk was that Elixir adds many things around the language. We have a lot of tooling to make it easier for the developer, to make the quality of life for developers easier. We try to make it easier for new developers to get started. It's very easy to generate a new project, for example. It's easy to start a shell with your application loaded and so on. And yeah, that's it. If you have any questions, I'm open for them. Yep.
So the Hex package manager.
Yep.
Will it be possible to easily set up a local index?
Okay.
Like at our company, we would like to have like a local repository since we have issues with GitHub. So.
Yep. Yep. So the question was if it's possible to set up a local registry for the Hex package manager. And that's not possible today because it's still so early in its life. But it's definitely something that we want to support in the future. In the future. Yep. Yep.
Actually, I have a solid question, but I'm limited to one. The notation and1, was that creating a partial function? It was like in the example for the actor. Anonymous function.
Yeah, here.
The actor one. Can you go to the actor one?
The extra one.
Yeah, for the atom one, sorry.
I'm not sure which example. The agent, yeah.
Sorry, so many things starting with n. You have this add_dict, which creates an anonymous function, I guess, and then add1. Is this creating an anonymous function with one argument, which will go there?
Yes. So the question is what this ampersand function means, and the easiest way to show it is to show the Erlang code that we also had. So if you look at this, it's a call to the put function on the dict module. The first argument here is the dict itself, the key and the value. And what this does is that it creates an anonymous function with one argument. So this is that argument. So if you look at the Elixir code here, it essentially creates a function that looks like this. Right, you see it? Yep. Any more questions? Yep.
Can you add Elixir to like an existing Erlang release? For example, like by just I don't know, adding some beam files to a release.
If you can add beam files to an existing release, no, I don't know of any tooling that does that. I think you would have to generate a new release, or, I mean, the Erlang tooling that works with releases most often works pretty straightforwardly with Elixir.
So the question was about how easy it would be to like add Elixir support to an existing project to you know like leverage the tools that you have in an existing Erlang project.
Okay, okay. So the question is how if you can add Elixir to an existing Erlang project, correct? And if this is easy. Yeah, you can add Elixir as a rebar dependency, and you can add your Elixir dependencies and so on with that, and it will be compiled, and it will just work with this syntax. Yep. Any more questions? Okay. Thank you.